All right, welcome back. We're going to now turn back to the intermediate goods firm and think about how they choose their prices given that they know that the bundler is going to demand this from them. So the reason why we took the detour into the bundler before returning to this firm is because we need to know this demand function. Now, the goal of the firm, as I mentioned previously, is to maximize its total expected profits over all of history, discounted, um, total discounted profits. So this is going to be profits for the jth firm, and it's going to be an expectation. It's going to be an expectation over an infinite sum from s equals 0 to infinity. We know what is profits. Profits are income minus cost. So income will be PJT times YJT, and it's going to be in period S. So PJT plus S, YJT plus S. And then from that, we subtract total cost in period for company J and period T plus S. Now, the question is how to discount this. And of course, immediately you should be thinking about beta to the S. But it's actually not enough to discount by beta to the S. We also have to think about how the shareholders, which are the households, think about consumption today and consumption tomorrow, because they want to use the firm to generate money in states of the world where they need money. Let me say that again. At certain time periods, consumption will be more valuable or less valuable. And in states where consumption is more valuable, they want more profit out of the firm. And the way that we measure the value of consumption in a state is with the Lagrange multiplier, with the shadow price. So this is why we're going to have this lambda t plus s divided by lambda t appear here. Taken all together, you should know that this beta to the s lambda t plus s divided by lambda has a name, and it's called the stochastic discount factor. Stochastic discount factor. And it just takes into account that when you do investment, you want to use investment to smooth your consumption. You want to move investment from from good states into bad states, so that the good states aren't so good, but the bad states aren't so bad. You want to use investment to smooth your consumption over time, rather than living in this boom bust. So for anybody doing finance, this won't be the last time you see this SDF, but for everybody else, now you know what it is. Total costs, we can also write in a more clever way. We know that total cost is, of course, equal to RK plus WL. But there's another way to think about total cost, which is it's the amount of stuff you produce times the unit cost of each thing that you make. And of course, we know the unit cost of each thing you make is the marginal cost. So we can write the total cost for firm J in time t as the marginal cost of JT times YJT, which is exactly what we'll do. We'll rewrite this. Is equal to the expectation of the infinite sum, s equals 0 to infinity, beta to the s, lambda t plus s over lambda t, p j t plus s y j t plus s, minus mc jt y jt. Okay, so now this is a valid function that will give you a firm decision. You could now go ahead and you could maximize by choosing pjt plus pjt, and then just maximize pi jt, and you would get an answer. Now we have a problem. The problem is that why did we do all of this? We did all of this not because we're interested in studying market power, which you could do by solving this setup. But we did this because we're interested in getting inflation. We want sticky prices. Right now, in this function, nothing prevents the firm from updating its price every single period. When there's a shock, it just changes PJT. And this is exactly what you're saying here. You'll get one equation, just like when you optimize the household, and you get one equation for CT, one equation for LT that works through all time. We would get that for PT, and we wouldn't have any inflation because every single period the firm would just update its price to be the new price, and everybody would update its price to be the same new price because we know that MCT is the same for everybody, and we know that lambda t is the same for everybody. And so we have no reason to suspect that YJT is going to be different for anybody, or that PJT is going to be different for anybody. So everybody chooses the same price and everything's the same, and we're done. So we need a way to introduce stickiness to the prices. And the way that we do that is via a Calvo rule. A Calvo rule. And a Calvo rule says that at each period, not all firms are allowed to update their prices. At each period, there's going to be a random signal. A random signal will arrive at each firm allowing them to update. Update their price. Okay, so the idea is you're a manager, you sit in your office. Every day you can get a phone call. And if you get the phone call, then you're allowed to change your price. Think of it as like a price setting board from the government or something. And this signal comes with probability 1 minus theta. BAB. Probability 1 minus theta. So every day there's a chance, theta, that you will not get the call. And if you do not get the call, your price stays the same. This is the whole setup. So what this means for our optimization problem now is that the firm has to plan for the worst case scenario. So consequence. When choosing price, when you get the call, you need to plan for the case that you never get the call again. So, how to think about this? This here is the best case scenario. In this case, you can update your price every day, no problem, and you will maximize pi JT. You will have the best possible pi JT. But you won't necessarily get that. What you might get is the worst case, which is you never solve it again. You never see the price again. What will that look like? That will look like we're going to maximize. Now we're going to maximize for a quantity I'm going to call PJT star, which will be this price we choose today and that we're going to have to be committed to forever. And the maximization problem is going to look very similar from s equals 0 to infinity. We're still going to have the stochastic discount factor. We're still going to have, this is part of it. But now, remember, we want to know the cumulative probability of every period s, t plus s, that we do not receive the phone call. So this is the worst case scenario. Every single time we don't get it. So the first period, we don't get it with probability theta. The second period, we won't get it with probability theta squared, theta cubed, theta fourth, and so on. So this is the worst case. And we multiply this by the same thing, total revenue, J T plus S, and we can never update our price again. So it's just going to be PJT star. And we subtract from that the marginal cost, J T plus S, times the amount of stuff that we make, YJ T plus S. So this is the worst possible case scenario. And by solving this worst possible case scenario, we get the best possible case scenario as long as we receive the signal. If we receive the signal every single day, and every single day we perform this computation, we will recover this best case. Because what we'll do is we'll just go back to the worst case, we'll solve it again, we'll get the answer that we would have gotten here, and then we'll just update it again tomorrow. Okay, so by solving the worst case, we get the best case in the best case, but we also cover our bases in all the intermediate cases. Okay, maybe that doesn't make so much sense, but this is the logic of why this problem emerges the way that it does. We're going to choose PJT in order to maximize the worst case scenario. And that's going to be subject to a known demand function. Of course, the demand function comes from the bundler's problem. So it's YJT, PT over PJT star. This is everything's plus S. So we know what demand is going to be in every single period. It's going to look like this. And we know that we're going to be locked into one price. So assuming that we lock in our price at PJT star, what will be the future demand at every single period? The expected future demand at every single period. So this is the hardest part of the new Keynesian model, is getting to this problem. I hope that talking through it helps you to understand what appears in here and why. Because knowing what to look for, remember there's a stochastic discount factor. Remember it's the worst case scenario. Remember that the call comes with, you miss the call with probability theta. Remember that this is just total cost. This is just total revenue. It'll help you to know if you've made any mistakes, copying the equation down. Okay. So now all that's left to do is to actually solve this maximization. And it looks bad because you have this infinite sum and all of this, but none of that matters. Okay. The only thing that matters, excuse me, is the part that's right in the inside here. So pause the video, have a try, and come back once you're done. Okay, you have it a try. Welcome back. Let's go. So we're going to maximize this infinite sum, but we know that the infinite sum doesn't matter, but we just have to kind of carry it all along with us. I'm going to begin by plugging in this here and looking for simplifications. Expectation at time t, sum from s equals 0 to infinity, lambda t plus s, lambda t, beta theta. I'll just move the s together, it doesn't matter. Okay, now I'm plugging in this form, pt plus s over pjt star phi. Yt plus s pjt star minus mcjt, and then the same expansion again, pt plus s over pjt star to the y times yt plus s. Oh, excuse me, this is all raised to the psi. Close parentheses, close bracket. Okay, right away, we know we're going to take a derivative. When we take derivatives, we have to face product rules, quotient rules. I do not want to do any of that. I do not want to do quotient rules. I do not want to deal with 1 over anything. So what I want to do is I want to rewrite all of these PJTs to be negative exponents, and I want to combine anything that I can. So I want to rewrite this one times this one, and rewrite this one so that it's 2 exponents. And I also see that I can do a factor, right? Because I have this and this and this and this are in both. So I'm going to factor all that out of the front, and I'm going to combine the PJTs, and I'm going to write them as without any division, just with negative exponents, because that's easier for me. An ounce of prevention is really worth a pound of cure in these problems. And I really, really recommend you to spend more time simplifying the problem and rewriting it to be more to your liking than you do actually taking the derivative. So this one and this one are exactly this and this. I just brought them up to the front. Now I'm going to have PJT star minus psi times PJT star is going to be PJT star to the 1 minus psi minus mcjt to the pjt minus psi. Okay, so now you see that this isn't such an awful derivative because, so we have infinite of these, fine. There's a t plus s here, but not there. So there's infinity of these, and we can't just factor out the PJT because it's being multiplied in two places, here and here. And there's two powers on it. If it was just one power, we could factor the whole thing out and we could ignore the entire infinite sum, but unfortunately we can't do that. So we just have to carry along the infinite sum, and we'll end up with one of these first order conditions. We'll end up with like one PJT term in every single sum, and so we can just pretend like the sum doesn't exist. Maybe that didn't make any sense. If you like write out a sum of, you know, 3 terms, if you write this out for 3 terms and look at the PJTs, you know, just look at t plus 1, t plus 0, t plus 1, t plus 2, and actually look at it and see how the derivative works, you'll see that you can just ignore the sum. And in the end, you'll be able to gather everything back together and rewrite it like this. Or you can just trust me. Pt plus s psi yt plus s. Here we get power rule. Power rule. I don't know why I can't say that word. I think I said product rule in a previous video when I meant power rule, so I was self-conscious. Minus 1, you get minus psi. Over here, we're going to get minus psi is plus. Yeah, plus mc jt plus s p jt star, this has a star as well, to the psi minus 1. Okay, am I happy with this? I'm happy with this. Okay, so now we're done with the derivative, and now we're actually almost done. We just need to do the tucking trick again, because you should see, or after you've done this problem a million times, you will see, should, what does should mean, right? That there's a PJT minus psi here, and there's a PJT minus psi here. So we can rewrite this by factoring out the PJT minus psi as this, lambda t plus s over lambda t, beta theta s. I'm going to put the minus psi back in here, so it's going to be pt plus s over psi. Or sorry, pt plus s over pjt star to the psi yt plus s times 1 minus psi plus psi mc jt plus s times pjt star to the minus 1. Okay, and now we have precisely yjt right here, so we can make that simplification. And all this equals 0 as well, because we finally took a derivative. So all this is equal to 0. We get the expectation at time t, the sum, s equals 0 to infinity, of lambda t plus s. We're almost there. T, yt, not yjt. Oh, no, this is yjt. I apologize. So this is yjt. This is the demand function. Times 1 minus psi plus psi mc jt divided by pj. We'll still write it as pjt minus 1 equals 0. Okay. So what can be done? We can split this sum into 2 sums. So what we really want to do is we want to get PJT isolated. We want one expression for PJT, and we're almost there. It's just that we need to split this into 2 infinite sums. So we're going to take this, this chunk here, and we're going to multiply it through here and here. And then we're going to rewrite the sum as 2 sums. And we can do that because everything has a t plus s, except for this t. So what we'll get is the expectation at time t, the infinite sum from s equals 0 to infinity, lambda t plus s over lambda t, beta theta s, y j t plus s, 1 minus psi. Okay, and then I'm going to split it, and I'm going to move out. So I have to multiply all this stuff again. So everything that's being multiplied, I have to multiply it again over here, and I can just write it again. And really, the only way that this will make sense to you is if you try it with a small sum. If you write this out for 3 terms, and you see that you're allowed to, by the rules of just addition and multiplication, break up the addition as long as you duplicate all of the multiplication. T plus s psi mc j t plus s p j t minus 1 close. I know my head's in the way of that. I apologize. I need to make space. Which means I have to erase. I'm sorry. Let me fix this. Okay. Select. Cut. Paste. Move. Okay, sorry. And let me write this a little nicer. This is psi mc j t plus s p j t star minus 1 equals 0. Now, we recognize that this, remember we said that psi was inside of 1 infinity, so this is negative. So let's flip it around so that it's clear that that's negative. Let's write this as psi minus 1 minus, and we can move the minus all the way out to the front. Anything that does not have an s can be canceled because it's just one multiplication, the same number multiplying every single thing in its sum. So we are allowed to move things that do not have an s outside of the infinite sum. So I'm going to move this minus to the other side, and I'm going to move everything without an s to the outside of the sum and the expectation. So there's this psi minus 1 that has no s. There's this lambda t that has no s. pjt has no s. Psi has no s. Lambda t has no s. So what we're going to end up with is, I'm writing this right part first. The expectation of t, sum from s equals 0 to infinity, lambda t plus s, beta theta s, y j t plus s, mc j t plus s, close. And then as promised, here is psi and lambda t and pjt minus 1. This is equal to this left side. And that's going to be the expectation of the infinite sum of lambda t plus s, beta theta s, y j t plus s, close. And then as promised, we have psi minus 1, lambda t. So we have a small cancellation. We can cancel lambda t and lambda t. We can also put all of these coefficients together. So let's bring this psi minus 1 over here. In fact, let's just divide this entire side over to the left, and let's move the pjt minus 1 to the right. So this will give us our final answer, which is pjt star is equal to, we're going to divide all of this to the left. So on the top, we'll have the expectation of the infinite sum. Let's start with the coefficients. Sorry, so we're going to have psi over psi minus 1 times the expectation at time t of the sum of s equals 0 to infinity, lambda t plus s, beta theta s, y j t plus s, mc jt plus s divided by the expectation at time t of the infinite sum from s equals 0 to infinity of lambda t plus s beta theta s y j t plus s. Boom. That is going to be the optimal price of the intermediate goods firms, given that they are not allowed to update their prices except when they receive the Calvo signal, which comes at probability 1 minus theta. It maximizes the discounted flow of profits to the firm, from the firm to the households, given the household preferences. Ta-da. You might be tempted to cancel. You might think you can cancel this and this. You cannot. And again, I keep encouraging you to think about a sum. So for this one, let's actually think about how you would do that. Let's think about all of this just being one term. Let's call it alpha 1. Okay, so if we have alpha I, so we'll say alpha 1 times x1 plus alpha 2 x2 plus alpha 3 x3. And on the bottom, we're just going to have the sum of the alphas. Alpha 1 plus alpha 2 plus alpha 3. So I'm saying that this lambda t plus s part, beta theta s, yjt plus s, that's shared, that's going to be called alpha, and I'm calling MC just as x here. Okay, so on the top I have the x's, and on the bottom I don't have the x's, but I have the same alphas on the top and the bottom. And you should see that there is no way to divide away these alphas, right? You could write this, you could split apart the division. You could write this as alpha 1 divided by alpha 1 plus alpha 2 plus alpha 3 x1 plus alpha 2, alpha 1, alpha 2, alpha 3, x2, and so on. And I think that's under my head. I apologize. Let me write it down over here. So you could write this as alpha 1 over alpha 1 plus alpha 2 plus alpha 3 x1 plus alpha 2 over alpha 1 plus alpha 2 plus alpha 3 over x times x2 plus alpha 2, alpha 3 over alpha 1 plus alpha 2 plus alpha 3 x3. But you cannot reduce this any further. And writing it like this is really nice because it shows us what do we have here. X is the marginal cost, and this alpha is this weighting term. So in each period, we're going to weight the marginal cost by that period's contribution to the total expected discounted flow of output. So at each period S, we're going to have some discounted expected output, yjt plus s. And then we also have the total sum of all of our outputs over all history. And so the contribution of each period's marginal cost to the total chosen optimal price is going to just be the fraction of that period's contribution to that total output. So I think written like this is actually quite nice. You can see really what this means. Figure out what your output is going to be for all history, and then weight your marginal cost by each period's output and add it all up to get the price that you're going to charge. Okay, so maybe this is an unsatisfying answer. You're hoping for something like nice and linear, but you don't get that with New Keynesian. And indeed, this is as far as we can go. There are techniques to solve this, and I think I might do a video on how to break this into two Bellman equations, and you can actually get a system of 3 equations that gives you a precise solution to this PJT star. But for the purposes of this class, you're done. There is also, typically what's done is you log linearize this, and you can see the techniques for how to do that in the readings for the class. So join me in the next video. I will finish the problem by figuring out what the total price index for the economy is going to be. And I'll see you there.